From H.G. Wells' Time Machine to the iconic DeLorean in Back to the Future, the concept of time travel has been a cornerstone of science fiction, sparking the imagination of countless readers and viewers. The idea of time travel has captivated our imaginations for over a century, inspiring a myriad of stories that explore the endless possibilities of moving through time. The allure of witnessing historical events firsthand or glimpsing into the distant future is a powerful one. Imagine standing beside great figures of the past or seeing the marvels of a future yet to come. But could such a fantastical concept ever be possible outside the realm of science fiction? Could we, one day, traverse the rivers of time as easily as we travel across the globe? While we haven't cracked the code to time travel just yet, theoretical physics offers some tantalizing possibilities. The equations and theories that scientists work on today might be the key to unlocking this age-old dream. Scientists have proposed several methods for how time travel might be achieved, each with its own set of challenges and implications. These methods range from the plausible to the highly speculative, but all share a common goal: to bend the rules of time. Two of the most intriguing concepts involve manipulating the very fabric of space-time itself. Wormholes, which are theoretical passages through space-time that could create shortcuts for long journeys across the universe, and the Alcubierre warp drive, a speculative idea that involves bending space-time to allow faster-than-light travel. These theoretical constructs, while still firmly in the realm of speculation, offer a glimpse into the mind-boggling possibilities that the universe might hold. They challenge our understanding of physics and push the boundaries of what we believe to be possible. Join me now as we delve into these concepts, exploring their potential and the hurdles that stand between us and the realization of time travel. Together, we'll journey through the theories and ideas that might one day turn science fiction into science fact. Imagine a shortcut through the universe, a pathway that defies the conventional limits of space and time. This pathway, often referred to as a tunnel, connects two distant points in space-time, creating a bridge that could potentially revolutionize our understanding of travel. This, in essence, is the concept of a wormhole, a fascinating and complex idea that has captured the imagination of scientists and science fiction enthusiasts alike. These theoretical objects are predicted by Einstein's theory of general relativity, a groundbreaking framework that has reshaped our understanding of the universe. According to this theory, gravity is not just a force but a curvature of space-time caused by massive objects bending the fabric of the cosmos itself. While we haven't observed wormholes directly, they offer a tantalizing possibility for traversing vast cosmic distances in a fraction of the time it would take to travel conventionally, potentially opening up new frontiers for exploration. Picture a piece of paper folded in half, with each side representing a different point in space-time. This simple analogy helps us visualize the complex idea of a wormhole. A wormhole would be like a hole punched through the paper, connecting those 2 points directly, bypassing the space in between. However, creating and stabilizing a wormhole would require exotic matter with negative mass energy density, a substance that behaves in ways that defy our current understanding of physics. This exotic matter is something we have yet to discover, and its existence remains purely theoretical at this point. Even if such matter exists, the engineering challenges involved in manipulating it to create a traversable wormhole would be immense, requiring advancements in technology and understanding that are currently beyond our reach. Another intriguing possibility for time travel comes in the form of the Alcubierre warp drive, a theoretical concept proposed by physicist Miguel Alcubierre in 1994. Instead of punching a hole through space-time, the Alcubierre drive envisions a spacecraft that manipulates space-time itself, creating a warp bubble around it. Imagine a surfer riding a wave. The surfer doesn't move through the water so much as the wave carries them along. Similarly, the Alcubierre drive would compress space-time in front of the spacecraft and expand it behind, creating a wave that propels the ship forward at potentially faster than light speeds. While mathematically sound within the framework of general relativity, the Alcubierre drive faces its own set of challenges. Like wormholes, it would require exotic matter with negative mass energy density to function. The energy requirements alone are staggering, estimated to be equivalent to the mass energy of Jupiter. One of the most perplexing aspects of time travel is the potential for paradoxes, situations where cause and effect break down, leading to logical inconsistencies. The most famous of these is the grandfather paradox. Imagine a time traveler journeying to the past and killing their own grandfather before their parent was even born. This action creates a paradox. If the grandfather died, the time traveler's parent wouldn't exist, and neither would the time traveler. But if the time traveler never existed, they couldn't have gone back in time to kill their grandfather in the first place. Such paradoxes have long been a thorn in the side of time travel theories, leading some to believe that time travel is inherently impossible. However, there are theoretical frameworks that attempt to address these paradoxes and maintain logical consistency. Section 5. The universe protects itself, the Novikov self-consistency principle. One such framework is the Novikov self-consistency principle, proposed by physicist Igor Dmitrievich Novikov in the 1980s. Novikov, a prominent figure in the field of theoretical astrophysics, introduced this principle to address the perplexing issues surrounding time travel and its potential paradoxes. This principle states that the universe has a built-in mechanism that prevents paradoxes from occurring. Essentially, it suggests that the laws of physics are structured in such a way that any event that would cause a paradox is inherently impossible. According to this principle, any action taken by a time traveler in the past was already a part of the timeline, even if they weren't aware of it at the time. This means that their actions are seamlessly integrated into history, ensuring that no contradictions arise. In the case of the grandfather paradox, the Novikov self-consistency principle suggests that the time traveler would be prevented from killing their grandfather, perhaps through a series of improbable but ultimately unavoidable events. These events could range from minor accidents to significant interventions, all conspiring to maintain the consistency of the timeline. While the Novikov self-consistency principle provides a potential solution to paradoxes, it also raises questions about free will and determinism. If every action is predestined to avoid paradoxes, then the concept of free will becomes murky. If our actions are predetermined to maintain consistency in the timeline, do we truly have the freedom to choose our own paths? This philosophical dilemma challenges our understanding of autonomy and the nature of the universe itself. The Novikov self-consistency principle, while offering a fascinating solution to time travel paradoxes, invites us to ponder deeper questions about our existence and the fabric of reality. Section 6. The energy of 1,000 suns. Even if we could overcome the theoretical hurdles of wormholes or warp drives, the energy requirements alone are staggering. Creating and maintaining distortions in space-time on the scale required for time travel would demand energy levels far beyond our current capabilities. To put it into perspective, the total energy output of the Sun over its entire lifetime is estimated to be around 10 to the power of 44 joules. The energy required for even a modest warp drive or traversable wormhole would likely dwarf this figure by orders of magnitude. Harnessing and controlling such immense energy would require technological advancements that are currently beyond our comprehension. It's like trying to boil the ocean with a tea kettle. The scale of the task is simply beyond our current means. Section 7. A House of Cards stability, concerns in time travel. Another significant challenge lies in the stability of wormholes and warp drives. These theoretical constructs are notoriously fragile, prone to collapse without constant maintenance. Imagine a tunnel dug through loose sand. Without supports in place, the tunnel would quickly cave in on itself. Similarly, maintaining the integrity of a wormhole or warp bubble would require a constant influx of exotic matter and energy, a delicate balancing act that could easily be disrupted. Even minor fluctuations in energy levels or the distribution of exotic matter could have catastrophic consequences, potentially stranding time travelers in the distant past or future, or leading to the collapse of the space-time structure itself. Section 8. A New Physics, the framework for paradox-free time travel. Recently, two physicists have put forth a new theoretical framework that attempts to address some of these challenges. Their model suggests that by incorporating elements of quantum mechanics into our understanding of gravity, we might be able to circumvent the paradoxes associated with time travel. This framework proposes that the universe doesn't follow a single, fixed timeline, but rather exists as a superposition of all possible timelines. Time travel, in this model, wouldn't involve changing the past but rather shifting our consciousness from one branch of the timeline to another. While still highly speculative, this new framework offers a tantalizing glimpse into how time travel might be possible, without violating the laws of physics as we understand them. It suggests that the universe might be even stranger and more wondrous than we ever imagined. Section 9. A journey still unfolding. The quest to understand time travel is ultimately a journey into the unknown. While we haven't cracked the code just yet, the pursuit itself has led to groundbreaking discoveries and pushed the boundaries of our scientific understanding. Whether time travel remains forever out of reach, or eventually becomes a reality, the exploration of this mind-bending concept will continue to inspire our imaginations and drive us to unravel the mysteries of the universe we inhabit. The universe is full of surprises, and who knows what wonders await us as we continue to explore the frontiers of knowledge. The journey of scientific discovery is never-ending, and the pursuit of knowledge is its own reward.